Flow of heat in geothermal activities. Geothermal activity means the natural heat activity inside the Earth. Earth's interior is much hotter than its surface, so heat moves from the hot inner layers toward the cooler crust. This heat appears in different forms such as magma movement, volcanic eruptions, hot springs, and tectonic plate activity. Structure of Earth and heat flow. To understand geothermal heat, we first look at the structure of Earth. Earth has four main layers: the crust, mantle, outer core, and inner core. The inner core and outer core are extremely hot. Heat from these deep layers slowly moves outward through the mantle and toward the crust. How heat moves. Underground heat. Inside Earth moves in three main ways. First, conduction transfers heat through solid rocks. Second, convection moves heat through hot magma and fluids. Third, radiation occurs when hot lava or heated surfaces give off heat energy. These processes together explain geothermal activities. Flow of magma. Beneath Earth, magma is molten rock found beneath Earth's crust. It collects in underground magma chambers. Because magma is very hot and less dense than surrounding rocks, it rises through cracks and weak pathways. As it moves upward, it transfers heat to nearby rocks and underground water. Magma flow, convection current. Inside the mantle, magma moves in convection currents. Hot magma rises because it is less dense. As it moves upward, it loses some heat and becomes cooler. The cooler magma becomes denser and sinks again. This cycle repeats continuously and carries heat through Earth's interior. Volcano eruption. A volcano eruption happens when magma rises toward the surface. Pressure builds inside the magma chamber. The magma travels through the central vent and reaches the crater. When it comes out, it is called lava. Ash clouds, gases, and lava release a large amount of heat to the surface. So volcano eruption and heat transfer. During a volcanic eruption, heat is transferred in different ways. Lava heats nearby rocks by conduction. Hot gases and molten material transfer heat by convection. Glowing lava also radiates heat energy outward. This is one of the clearest examples of geothermal heat reaching Earth's surface. Movement of tectonic plates. Earth's crust is divided into large pieces called tectonic plates. These plates move slowly over the mantle. The movement is helped by convection currents in the hot mantle. As hot material rises and cooler material sinks, it pushes the plates in different directions. Plate boundaries and geothermal activity. Geothermal activity is common near plate boundaries. At divergent boundaries, plates move apart and magma rises to fill the gap. At convergent boundaries, one plate may sink beneath another and melt. These regions often have volcanoes, earthquakes, hot springs, and other geothermal features. Earth core maintains its temperature. Earth's core remains extremely hot because heat is produced and trapped inside. The heat escapes very slowly toward the surface. The crust acts like a protective outer layer, while the mantle and core store large amounts of thermal energy. Several factors help Earth maintain its internal temperature. Residual heat. From formation. One important source of Earth's internal heat is residual heat from formation. When Earth formed billions of years ago, dust, rocks, and other materials collided and compressed together. These collisions produced a huge amount of heat. Some of that original heat is still stored deep inside Earth. Radioactive decay. Another source of heat is radioactive decay. Some elements inside Earth, such as uranium, thorium, and potassium, are radioactive. Their unstable atoms break down naturally. During this process, radiation and particles carry energy away from the nucleus. This energy becomes heat inside Earth. Gravitational compression. Gravitational compression also helps keep Earth hot. Gravity pulls Earth's deep layers inward, creating enormous pressure. This pressure squeezes materials inside Earth. As the materials are compressed, their internal energy increases, which helps maintain the high temperature of the core. Crust as an insulator. The crust acts like an insulating blanket around Earth's hot interior. Rocks in the crust do not conduct heat very quickly, so heat escapes slowly. Because of this slow heat loss, Earth can keep much of its internal heat for a very long time.